For Mercedes-Benz, Formula One is the perfect laboratory for developing state-of-the-art technology. The new rules call for major improvements in energy efficiency. Each car may now use just 100 kilograms of fuel per race, equivalent to around 130 litres, which means it must now deliver top performance on 1/3 less fuel. It is achieved with a downsized 1.6-litre turbo hybrid engine. The turbo uses exhaust gases to drive a compressor to push more air and therefore more oxygen into the engine. Together with high-pressure direct fuel injection, this makes combustion more efficient, more power using less fuel. Another challenge is increased heat in the more compact engine. Mercedes partner Petronas was integral to the development of the power unit and has created an oil that seems to reverse the laws of physics. As it heats up, Petronas Syntium gains in density instead of getting thinner, protecting the engine even under the greatest loads where other oils fail. The engine is boosted by a hybrid system made up of 2 electrical motor generators to recycle energy that would otherwise be lost. The MG UK delivers up to 160 horsepower for 33 seconds per lap, equivalent to a Mercedes C220 CDI. Connected to the braking system and acting as a generator, the MG UK can feed so much energy into the battery every lap that you could talk for 370 hours on your BlackBerry smartphone. The second motor generator unit, the MG UH, harvests the turbo energy. As a motor, it spins up the compressor to eliminate turbo lag, but it can also send energy directly to the other electric machine and vice versa for maximum efficiency. However, the main job for both electric machines is to deliver energy to the lithium-ion batteries. These must weigh between 20 and 25 kilograms. Low weight and constant charging and discharging are major challenges. At Mercedes, the development process produced new learnings for road car battery production. Overall, the new power unit is over 30% more energy efficient. So if you use this technology in your road car, it would cost you just €40 to fill your tank instead of €60, and you would enjoy more performance too. The PU106A hybrid power unit, state-of-the-art technology at the heart of the winning Mercedes F1 W05 hybrid race car. The 2014 power units consist of a 1.6-litre V6 internal combustion engine that is rev-limited to 15,000 RPM, a turbocharger which exists to get more air into the engine and create more power, and an energy recovery system known as ERS. The ERS features an energy store which, like a battery, retains energy recovered, then uses it to propel the car using the MGU Kinetic, one of 2 motor generator units. This is attached to the engine crankshaft and converts kinetic energy recovered under braking into electrical energy. It provides a potential 160 brake horsepower performance boost for around 30 seconds, far more than the previous KERS systems. The MGU heat is connected to the turbocharger and converts heat or exhaust gas energy into electrical energy. This energy can be stored or sent directly to the MGU Kinetic to be used instantly. All of this will be regulated by the control electronics, known as the brain of the car. This has huge implications for the racing strategy and driving style in 2014. Under acceleration, the MGU heat can act as a generator. It can recover energy from the exhaust and send it directly to the MGU Kinetic or to the energy store. The MGU Kinetic will act as a motor and deliver additional power to accelerate the car or save fuel, depending on the chosen strategy. The MGU Kinetic operates as a generator unit, capturing some of the kinetic energy wasted under braking. To recharge the energy store unit, this is similar to KERS. On the exit of braking, the MGU heat briefly acts as a motor to accelerate the turbo to its optimum speed to prevent what is traditionally known as turbo lag. Over the course of a lap, the driver will have managed the harvesting of energy. This can be called upon to increase the power output of the internal combustion engine, for example, to overtake. The driver now has 120 kilowatts or 160 horsepower of extra boost available for around 30 seconds, compared to 60 kilowatts or 80 horsepower for 7 seconds from last season's KERS. Formula One is now using around 1/3 less fuel without compromising on speed or power.
When the driver puts his foot on the throttle.
Welcome to a new era in Formula One. Ushering in the new V6 turbocharged units has not been an easy process, with pre-season proving to be fraught with technical complications. So in this video, with the help of some graphics from Renault Sport F1 and Red Bull Racing, I hope to clue you in on some of the changes faced by the teams for 2014. This video will deal exclusively with the power units, rather than the raft of aerodynamic regulation changes, and hopefully not only explain some of the aspects you're already aware of, but fill in some of the blanks. So let's start off by explaining some of the fundamentals. Gone are the naturally aspirated 2.4 litre V8s, replaced by 1.6 litre V6s we refer to as the ICE. That stands for Internal Combustion Engine. For the first time, Formula One uses direct injection, with the fuel injected directly into the cylinder head, leading to a better stratification of the fuel and in turn providing more efficiency and power. This downsizing of the ICE leads Formula One back down the turbocharged path, with a singular turbo arranged around the car's centreline providing boost that was last seen in F1 in 1988. Fuel is limited during the race to 100 kilograms, which is roughly 140 litres, whilst the maximum fuel flow rate of 100 kilograms an hour is also closely monitored by the FIA. The ICE has a maximum rev limit of 15,000 RPM, down on the 18,000 RPM of the outgoing V8s. The allotted revs are unlikely to be reached, however, with a fuel flow restriction placed at 10,500 RPM. The reason we call them power units is they are now complemented by two energy recovery systems, known as the MGU-K and MGU-H, both of which are motor generator units. The MGU-H, where H stands for heat, is attached via a shaft to the turbo and recovers wasted energy or provides assistance to keep the turbo spooled when the boost pressure drops. The MGU-K, or K, is a beefed up version of KERS that was tacked onto the V8s in 2009. This provides a maximum of 120 kilowatts or 160 horsepower, rather than its predecessors 60 kilowatts or 80 horsepower. One of the areas that seems to have been talked about incorrectly thus far is the way in which the K releases power throughout the lap. When we had KERS, energy was only released when the driver pressed a button on the steering wheel, but the K is intrinsically mapped to the accelerator pedal for 2014. This means the maximum 4 megajoules of energy available from the energy store throughout the lap is provided based on how the driver applies the throttle. The graduation of power means that the K can provide much more than the 33.33 seconds of energy per lap that most of the outlets are reporting. In other words, the more throttle you apply, the more energy the K will supply. The K's other job is to recover energy under braking, of which 2 megajoules can be held in the energy store. This is 5 times the amount of energy that KERS used to harvest. More still can be harvested and passed directly to the H to keep the turbo spooled. All of this puts a new emphasis on brake bias and requires the ECU to calculate how much braking is being done at the K, how much the bias that the driver has selected, and then how much mechanical braking must be done at the rear of the car. You will hear this referred to as brake-by-wire. This leads to some complex software code to be written and is the subject of many discussions between the drivers and their engineers. Some of the teams and drivers are pleased with the results, but others are having massive difficulties, with a lack of feel being the largest gripe. The FIA's energy flow diagram explains that energy can pass both ways between the H and the K without need to be stored and without restriction. As the season matures, it will become obvious that the teams are maximising this opportunity, as the fluidity of energy transfer during high and low speed transitions will result in more performance. For instance, as the driver lifts off the throttle to brake for a corner, the K starts harvesting energy, shown here in blue, and will either send it to the controller, with the electrical energy being retained as AC, that's alternating current, and then be passed to the H, shown in red, to keep the turbo spooled, or the energy from the K can be converted to DC, that's direct current, and that's stored in the ES for later use. If the K is recovering too much energy, both flow schemes will happen, with the K feeding the H and the ES. Furthermore, there are instances where the energy being recovered exceeds the requirements of the MGUs, or motor generator units, H or K, and cannot be converted quick enough to be stored, and so the teams have heat sinks, which will dissipate the additional heat. Although their primary job is to dissipate heat that is wasted in the transfer of energy from AC to DC or DC to AC. Pictured here is a heatsink you may be familiar with, as it sits astride a computer's processor. A similar process is taking place within the F1 car. When the driver picks up the throttle, the transition between the K harvesting power and delivering power begins again, with the teams able to control this in harmony with the pedal map. Meanwhile, the turbo might start to produce a little too much boost pressure, and so the H will harvest energy by slowing it down, shown here in blue. This energy can either be sent to the K through the controller in DC form, and therefore isn't subject to the maximum 4 megajoules supplied by the ES per lap, extending its performance, or it can be converted to AC energy and stored in the ES for deployment later in the lap. As the driver continues to accelerate through the gears, of which there is 8 ratios for 2014 and must be selected at the start of the season and then retained throughout, boost pressure is once again monitored by the H. As speed builds and the boost threshold is exceeded, the H will begin harvesting the energy and passing it directly to the K through the controller, once again boosting the amount of time the K can operate outside the ES's deployment limitations of 4 megajoules. Hopefully you can now see that the electrical energy flow of the new power units is complex when compared to the outgoing KERS package. As the season progresses, we'll undoubtedly see teams reap the rewards of these complexities as they extract additional performance.
In 2014, F1 enters a new era. For the first time in the history of the sport, cars will be powered by both fuel and electrical energy, produced by Avant-Garde power units. No longer just an engine, the power units combine turbocharged V6 internal combustion engines with powerful energy recovery systems. 2 motor generator units, or MGUs, harvest energy from heat in the exhaust and recover mechanical energy during braking. The systems work in harmony, with cars balancing the 2 types of energy throughout the race. Both MGUs are coupled to the turbo engine and packaged within the chassis. Under acceleration, the internal combustion engine works at full speed, with the turbocharger rotating at close to 100,000 RPM. The MGU H for heat, works as a generator and recovers energy from the exhaust, which exits from one centrally located exit. This energy is passed either to the battery store, where it will be stored for use later in the lap, or to the MGU-K, K for kinetic. The MGU-K, which is connected to the crankshaft of the engine, acts as a motor and delivers additional power. When the driver brakes at the end of the straight, the MGU-K converts to a generator and recovers energy from the braking event. This energy will be stored in the battery for later use in the lap. After a hard braking event, engine speed drops and the rotational speed of the turbo also falls. To avoid turbo lag when the driver gets back on the power, the MGU-H acts as a motor to keep the turbo turning at high speed. Such complex exchange of energy is controlled by electronic control systems, with certain driver-operated modes to allow strategic flexibility and occasionally a boost of power when overtaking. Potent energy recovery systems and restrictions on fuel flow rates and quantity put in the power units are amongst the most energy efficient in the world. The Renault Energy F1, a new power unit for a new era.
Lotus's ground effects, Red Bull's blown diffuser, Williams' active suspension. All of these engineering masterstrokes providing their teams with an individual advantage over their competitors. In 2014 there seems to be one team though with a major edge over the others, Mercedes-Benz of course. This week, a story broken by Mark Hughes of Motorsport magazine and Sky F1 has uncovered the truth behind their early dominance and shed light on a truly revolutionary piece of F1 science. So what is it? First, we must understand how a turbo works. There are two main components to a turbo, a turbine and an air compressor. These are sat next to one another at the rear of the engine. Why the rear? Well, as the exhaust fumes leave the engine, they power the turbine, in turn powering the compressor. This process generates a great deal of heat, and before the air can be fired into the engine it must be cooled. This takes place in the car's intercoolers, these are located in the side pods of each car. By the time the air passes through this pipework it's cool enough to enter the engine and help with combustion, and so increase the horsepower generated. The cycle starts again. Now Mercedes' engineering feat has come by separating their turbine and compressor. The turbine is still located near the exhaust, but they've moved the compressor, locating that at the front of the engine, connecting it up by running a shaft through its centre. A simple idea, but a very advanced piece of engineering that's generated many benefits. Firstly, the compressor is now cooler, it not being next to the turbine and being nearer the air inlet above the driver's head. So there's less pipework needed for the intercoolers to do their work before the air gets fired into the engine. This has two benefits of its own. It reduces turbo lag, as the air is not travelling through as much pipework. So the engine is already relying less on its ERS unit to eliminate turbo lag, putting it to better use elsewhere. Secondly, therefore, the car's smaller intercoolers can reduce the size of the side pods, giving the car less aerodynamic drag. But the rewards don't stop there. Having moved the very hot compressor to the front of the engine, the rear is now cooler, and the complex gearbox can now safely be housed almost underneath the turbo. This helps with the car's balance. All the major weight is now in a more centralised area, allowing for better change of direction. It also means that the whole engine unit is more compact. If you look at the rear of the Mercedes, you'll see there are two blister-like objects. These are there just to meet the regulations, and this image gives you an indication of just how much thinner the rear of the Mercedes is compared to its competitors. So, one simple idea has cascaded into many others, giving the Mercedes more power, less drag, and a much faster car.